Okay, so we're just looking at this idea of independence and events being independent. We can do this very statistically, looking at the probabilities of two things being independent of each other. What independence means um, is independence just is talking about like one event not affecting another event. So, like the outcome of something is not going to change the probability of another thing occurring. Okay. Um, Again, that's what it means for two events to being independent. That the that one event does not affect the outcome of another one. So, whoops, we're in that room. Okay, so, whoops, come on now. Computer problems right now. So one example of this would be like getting a heads on the first, like 5 flips of a coin. That still doesn't affect whether we get a heads on the 6th one. Those are independent events. Flipping coins are always resetting all the time. So it just keeps resetting, and so one event does not affect another one. Rolling coins is often, or sorry, rolling a die, not rolling coins. So rolling a die also is another one of those things that is independent, because what I get on one roll does not affect the outcome or the probability of another one. So those would be a couple of examples here. What we want to do is be able to take events and be able to determine if they're independent or not. So let's just start with this. So for example, let's say we select a card from a shuffled deck of cards. You return the card and shuffle and select another card. And both times the card is diamond. So we're wondering if getting a diamond on the first one or the second time is independent. This would be independent. And the reason being is because we shuffle and return the card. So whenever we return it and shuffle it back up, that would be independent. Let's say I've got a bag of marbles here. I'm going to pick a marble and then pick a second marble without returning that to the bag. This would be dependent because I don't return it back to the bag, is essentially what the problem is with this one. Okay. Again, it's affecting the next outcome. Like we have one less marble essentially. So for the next one, I've got 6 nickels, 4 dimes in my pocket, but I randomly pick a coin out of my pocket and place it on the counter. And then I pick another one, and both coins are nickels. This would also be dependent because I put it on the counter. I don't put it back in. So it's all about putting it back in or resetting every single time. And then this last one, flipping coin, we've actually already talked about this one, and getting a tails, and then getting a heads on the next one. These are independent because I'm flipping the same coin. It resets it every time. So it's all just based on whether or not we reset or don't reset is what we're looking for here. Okay. A little bit harder when we're looking at a two-way table is like idea of independence. For example, I've got this table of boys, girls, and what language class they're in, or they took. And so we asked the question, determine whether a person who took Spanish and a person that's boy is if they're independent. So this first event is whether they took Spanish. We'll just call that event A. And being a boy would be event B. Okay. To prove that things are independent, I'm going to use this nice little equation. I'm going to find the probability of A and B, which we did on a previous thing. And then I'm going to find the probability of just A, and I'm going to times it to the probability of just B. So if I'm going to times those two together as well. And then if these two things are equal, then we're going to say that they are independent. If they're not, then they are dependent at that point in time. Okay? So if I look at this first one, I got event A is having a person take Spanish, and then event B is a boy. So the probability of selecting a person that's in Spanish class and they're a boy, that's just that overlap. So I'm going to look at that. So that would be boys that took Spanish. That'd be 10 out of 50. Okay. And we actually want to put that as a percentage. So 10 divided by 50, which gives me 0.2. So that gives me a 20, again, 0.2, which gives me 20%. Okay. And then what I want to do is I want to look at probability of A, or somebody took Spanish, and I'm going to times it by the probability that they are a boy. So that would look like this. Probability that person took Spanish, that would be the 25 out of 50. So that's 25 out of 50. And then I'm going to times it to the probability that I can select a boy, which should be 20 out of 50. So 20 out of 50 for this. And then I'm going to times those two together to get my probabilities for this. So this would be 500 over 2500. And so when I divide those, that gives me a 0.2 or 20%. So I would say that these are indeed independent because I've got 20% here and I've got 20% here. And that's how we look at that. Okay. Look at one more here. So let's say determine if a girl and a person taking German. So a girl is event A and person taking German is event B. So I first find the probability of A and B occurring. So girl and German. So I go girl and German, that would be the 3 out of 50. And then I can put that as a percentage. When I put that as a percentage, I get 0.06, which would give me 6%. Okay, and then I'm going to find the probability of A and times it by the probability of B, which that would just be the probability of selecting a girl. There are 30 girls out of 50, so that would be 30 out of 50. And then event B is somebody being in a German class, so that'd be 11 out of 50. So 11 out of 50. And so I'm going to times those two together. And so this one I get 330, and then I've got 2,500 here again. And so I end up getting 0.132, which should be 13.2%. So these are different, so I would say these are actually dependent if you look at it mathematically that way. So, okay, that's how we look at that. That's how we find out if something's independent of each other. So, all right, Math Moment with Mommy out. Bye.